what happens after the universe ends. Not what happens when a star dies or when a galaxy fades, but what happens after the entire cosmos has run out of everything it needs to function. This is not a question about religion or imagination. It is a question that physicists take seriously, calculate carefully, and argue about in peer-reviewed journals. The universe had a beginning, and the evidence for that beginning is overwhelming. If something began, it is reasonable to ask how it might end, and what, if anything, comes next. For most of human history, the cosmos was assumed to be eternal and unchanging. That assumption collapsed in the 20th century. We learned that space itself is stretching, that galaxies are flying apart, and that the universe was once compressed into a hot, dense state we now call the Big Bang. Once you accept that the universe has a history, you are forced to confront its future. And the future, according to our best measurements, is far stranger than the past. There are several possible endings. The universe could expand forever until it grows cold and empty. It could be torn apart. It could collapse back on itself. It could even reset and begin again. Each of these outcomes is built on real physics, real observations, and real equations. Some of them lead somewhere afterward. Some of them lead nowhere at all. This is an investigation into the deep future, far beyond the lifespan of any star, any planet, or any living thing. We will follow the evidence as far as it goes, and then we will follow the speculation that begins where the evidence ends. To understand how the universe might end, we first have to understand what it is doing right now, because the ending is already written into the present motion of everything around us. The story begins with a discovery that seemed almost impossible when it was first confirmed, a discovery that overturned decades of careful assumptions and forced cosmologists to rewrite their predictions about the deep future. For most of the 20th century, astronomers knew that the universe was expanding. This was established in the 1920s when Edwin Hubble, working at the Mount Wilson Observatory, measured the light from distant galaxies and noticed something consistent and strange. The light from nearly every galaxy he observed was shifted toward the red end of the spectrum, and the more distant the galaxy, the greater the shift. This redshift was the fingerprint of motion. The galaxies were moving away from us, and they were doing so in a pattern that suggested space itself was stretching, carrying the galaxies along with it, like raisins embedded in rising bread dough. The dough expands, and every raisin moves away from every other raisin, not because the raisins are traveling through the dough, but because the dough between them is growing. This was a profound realization, but it raised an immediate and obvious question. If the universe is expanding, what is the expansion doing over time? Common sense and the physics of the era suggested that the expansion should be slowing down. The reason was gravity. Every galaxy, every star, every particle of matter in the cosmos exerts a gravitational pull on every other piece of matter. That collective pull should act like a brake, gradually decelerating the outward rush of the galaxies. The only real question seemed to be whether there was enough matter in the universe to eventually halt the expansion entirely and reverse it, or whether the universe would coast outward forever, slowing but never quite stopping. For decades, this was the central debate in cosmology. Researchers tried to weigh the universe, to measure its total density of matter, because that number would determine the ending. Enough matter and gravity wins, pulling everything back together. Too little matter, and the expansion continues indefinitely, thinning out across ever greater distances. In the late 1990s, two independent teams of astronomers set out to measure precisely how much the expansion was slowing down. They were not questioning whether it was slowing. They simply wanted to measure the rate of deceleration with greater accuracy than ever before. To do this, they needed a reliable way to measure enormous cosmic distances, and they found it in a particular kind of stellar explosion known as a Type 1a supernova. These explosions occur when a dense stellar remnant, called a white dwarf, accumulates too much material from a companion star and detonates. The crucial property of these supernovae is that they all explode with very nearly the same intrinsic brightness. Because the true brightness is known, astronomers can compare it to the brightness observed from Earth and calculate exactly how far away the explosion occurred. A dimmer supernova is more distant, a brighter one is closer, and the relationship is precise enough to serve as a cosmic measuring stick. These objects are called standard candles because their consistent luminosity lets us gauge distance across billions of light years. The teams collected light from dozens of these distant supernovae, some of them so far away that their light had traveled for billions of years before reaching the telescopes. By combining the distance derived from each supernova's brightness with the redshift that revealed how fast it was receding, the astronomers could reconstruct the history of cosmic expansion. They could see not just how fast the universe was expanding now, but how fast it had been expanding in the distant past, when that ancient light first set out on its journey. The plan was elegant, and the expectation was clear. The data should show that expansion was faster long ago and slower today, the signature of gravity gradually applying its brakes. The data showed the opposite. The distant supernovae were fainter than they should have been if the universe had been decelerating. They were farther away than a slowing expansion could account for. The only way to make sense of the measurements was to conclude that the expansion of the universe was not slowing down at all. It was speeding up. Somewhere in the last several billion years, the universe had shifted gears, and the galaxies were now accelerating away from one another, the spaces between them growing at an ever-increasing rate. Both teams arrived at this conclusion independently, checking and rechecking their work, because the result was so contrary to expectation that no one wanted to announce it without certainty. When the findings held up, they represented one of the most significant discoveries in the history of science, eventually recognized with a Nobel Prize, and they fundamentally changed the projected fate of the cosmos. To appreciate how unsettling this was, consider what acceleration implies. Throwing a ball into the air, we expect it to slow, stop, and fall back, pulled down by gravity. Imagine instead throwing a ball upward and watching it speed up as it rose, climbing faster and faster into the sky, as though something were actively pushing it away from the ground. That is essentially what the universe is doing. Some influence is overpowering the collective gravity of all the matter in existence and driving everything apart with growing force. Whatever this influence is, it does not behave like matter. It does not clump together. It does not dilute in the simple way ordinary energy does, and it appears to be woven into the fabric of space itself. The more space there is, the more of this influence there seems to be, which is why its effect grows stronger as the universe expands and creates ever more volume for it to inhabit. This discovery did more than win prizes and rewrite textbooks. It transformed the question of how the universe ends from a debate about the amount of matter into a debate about the nature of this unknown driving force. Before the discovery, the future seemed to hinge on a tug-of-war between expansion and gravity, with gravity as the only major player capable of changing the outcome. After the discovery, it became clear that a third factor, far more powerful than ordinary gravity on the largest scales, was in control of the cosmic destiny. The fate of everything would be decided not by how much matter the universe contained, but by how this mysterious accelerating force behaved over the immense stretches of time still to come. If it remained constant, the universe faced one kind of ending. If it grew stronger, it faced another, far more violent conclusion. If it somehow weakened or reversed, yet another path opened up. What made the situation even more remarkable was the realization of how recently, in cosmic terms, this acceleration had taken over. For the first several billion years after the Big Bang, matter was densely packed, gravity was the dominant influence, and the expansion did indeed slow down, just as the old models predicted. Only later, as the universe expanded and matter spread thin, did the accelerating force gain the upper hand and begin to dominate. We happen to live in the era of the handoff, the cosmic moment when deceleration gave way to acceleration. This timing struck many scientists as curious, perhaps even suspicious, and it raised questions about whether the force was truly constant, or whether we simply caught it during a particular phase of a longer evolution. The answer to that question, still unresolved, carries enormous weight, because it points toward radically different futures, depending on which interpretation proves correct. The measurements have only sharpened since those first supernova surveys. Observations of the faint afterglow of the Big Bang, the pattern of galaxies spread across the sky, and the subtle bending of light by massive structures have all converged on the same conclusion. The universe is accelerating, and the force responsible accounts for the majority of the total energy in the cosmos. Ordinary matter, the stuff of stars and planets and people, is a minor ingredient. The familiar universe of light and substance turns out to be a thin layer floating atop something vast and unseen, something that determines not only how the universe behaves today, but how it will meet its end. We have measured its influence with growing precision, yet we still cannot say what it actually is. And until we understand its nature, every prediction about the deep future remains provisional, balanced on the properties of a force we have detected everywhere, but identified nowhere. That force has a name, though the name is more a placeholder than an explanation. We call it dark energy, and the word dark here does not refer to color or to anything ominous. It signals ignorance. We call it dark for the same reason we speak of dark matter, because it does not emit, absorb, or reflect light, and because we know it primarily through its effects, rather than through any direct observation of the thing itself. Dark energy is the label we attach to whatever is driving the accelerating expansion of the universe, and attaching a label to it has not brought us much closer to understanding what it is. We know it is there. We know roughly how much of it exists, and we know what it does. We do not know why it exists or what it is made of, and that gap in our knowledge sits at the very center of every attempt to predict the cosmic future. The first thing to grasp about dark energy is just how much of it there is. When cosmologists tally up the total contents of the universe, they find that ordinary matter, everything composed of atoms, every star and planet and cloud of gas, accounts for only a small fraction of the whole, somewhere around 5%. Dark matter, The unseen substance whose gravity holds galaxies together makes up a larger portion, roughly a quarter. The remaining majority, close to 70% of everything, is dark energy. This means that the universe we can see, the luminous cosmos of stars and galaxies that fills our telescopes, represents a tiny sliver of the actual energy budget. We are like sailors who have charted only the surface foam, while the vast bulk of the ocean remains hidden beneath. The dominant component of reality is something we cannot see and barely comprehend, and it is precisely this dominant component that holds the future in its grip. The second thing to understand is how dark energy behaves, and here is where it reveals its strangeness. Ordinary matter dilutes as the universe expands. Take a fixed amount of matter and spread it across a growing volume, and its density falls, because the same quantity of stuff now occupies more space. Radiation behaves similarly, thinning out and losing energy as space stretches. Common sense would suggest that any form of energy should weaken as the cosmos grows, simply because it has more room to fill. Dark energy refuses to follow this rule. As far as we can tell, its density stays constant. Double the volume of space, and you do not get the same amount of dark energy spread thinner. You get twice as much dark energy in total, because each region of space seems to carry its own fixed allotment, and creating new space appears to create new dark energy along with it. This is the property that makes dark energy a property of space itself, rather than something residing within space. It is not a substance floating in the vacuum. It appears to be a feature of the vacuum. This constant density has a remarkable consequence for the long-term behavior of the universe. In the early cosmos, when everything was densely packed, matter and radiation dominated, and their gravitational pull governed how space evolved. But as the universe expanded and matter thinned out, the influence of matter faded, while the influence of dark energy held steady. Eventually, the constant pressure of dark energy overtook the dwindling pull of matter, and that is the transition we discussed earlier, the handoff from deceleration to acceleration. The crucial insight is that this trend is self-reinforcing. As dark energy drives the universe to expand faster, it creates more space. And more space means more dark energy, which drives the expansion faster still. The process feeds on itself. Unlike matter, which loses its grip as the universe grows, dark energy only tightens its hold. This is why, if dark energy behaves as a true constant, the future of the universe is one of relentless and unstoppable acceleration. The idea that empty space could possess energy is not as outlandish as it first appears, and it has roots that reach back further than the supernova discoveries. Albert Einstein, working through the equations of general relativity in the early 20th century, found that his theory of gravity allowed for a term that represented a kind of energy inherent to space itself. He called it the cosmological constant, and he originally introduced it for reasons that had nothing to do with acceleration. At the time, the universe was assumed to be static, neither expanding nor contracting, and Einstein needed a way to counterbalance gravity, which would otherwise cause a static universe to collapse. The cosmological constant provided an outward push that could hold the cosmos in equilibrium. When Hubble later demonstrated that the universe was expanding, the need for a static balancing act vanished, and Einstein reportedly regretted ever introducing the term. Yet the mathematical possibility never disappeared, and decades later, when astronomers discovered acceleration, the cosmological constant came roaring back as the simplest candidate to explain it. The energy of empty space, once introduced to keep the universe still, turned out to be exactly the kind of thing that could drive it apart. Modern physics offers a tempting explanation for where this energy of empty space might come from, though the explanation comes wrapped in a deep and embarrassing problem. According to quantum field theory, the vacuum is not truly empty. At the smallest scales, space seethes with activity, with particles and their antiparticles constantly flickering into existence and annihilating one another in fleeting bursts. These quantum fluctuations are not merely theoretical. Their effects have been measured in laboratories, in subtle shifts of atomic energy levels, and in tiny forces between closely spaced metal plates. If the vacuum is full of this restless activity, then it should carry energy, and that vacuum energy is a natural candidate for dark energy. The problem is one of scale. When physicists attempt to calculate how much energy the quantum vacuum should contain, they arrive at a number staggeringly larger than the amount of dark energy actually observed. The mismatch is not small. It is one of the largest discrepancies between theory and observation in all of science, a gap so enormous that it signals something deeply wrong with our understanding. Either the calculation is missing some crucial cancellation that brings the number down, or vacuum energy is not the source of dark energy at all, or our grasp of how gravity responds to energy at the quantum level is incomplete. This is why dark energy remains such an open and pressing question. We have a leading candidate, the cosmological constant, that fits the observations well and predicts a constant energy density consistent with everything we measure. But we lack a satisfying explanation for why it has the value it does, and the most natural theoretical source for it gives an answer that is wildly wrong. This uncertainty is not merely an academic inconvenience. It bears directly on how the universe ends. If dark energy is truly a cosmological constant, fixed and unchanging for all time, then the universe will continue accelerating at a steady pace, leading to one particular fate. But there are alternative ideas. Some physicists propose that dark energy is not a constant at all, but a dynamic field, something that can change in strength over cosmic time. In these models, dark energy might weaken in the future, or it might grow stronger, and each possibility leads to a dramatically different ending. A weakening dark energy could allow gravity to reassert itself. A strengthening dark energy could accelerate the universe so violently that it tears apart everything within it. The instruments now turning toward the sky are designed in large part to settle this question by mapping the distribution of galaxies across enormous volumes of space and tracking how the expansion rate has changed. Throughout cosmic history, astronomers hope to determine whether dark energy is constant or evolving. The difference between these scenarios is measured in subtle variations, in slight deviations from the steady behavior a true constant would produce. Early hints from some of these surveys have suggested, tentatively, that dark energy might not be perfectly constant after all, that its strength may have shifted over the ages. If those hints hold up under scrutiny, they would transform our picture of the cosmic future and open the door to endings that a simple cosmological constant would forbid. For now, the measurements remain uncertain, and the cautious conclusion is that we do not yet know whether the force driving the universe apart is eternal and fixed, or changeable and capable of surprising us. What is certain is that dark energy, whatever its true nature, has become the single most important factor in determining how everything ends. The ancient debate about whether there was enough matter to halt the expansion has been settled, and matter lost. The cosmos is not going to be reined in by the gravity of its own contents, at least not under current conditions. Instead, the outcome depends entirely on the behavior of this unseen, unexplained majority of the universe. And because we cannot yet say whether that behavior is steady or shifting, we are left with not one prediction for the end of everything, but several, each tied to a different assumption about the force we understand least. The shape of the cosmic ending, it turns out, is not a single fixed destiny, but a branching set of possibilities. And which branch the universe follows depends on a question we have only begun to answer. Faced with this uncertainty, cosmologists have done what scientists always do when confronted with an unknown that resists direct measurement. They have mapped out the range of possibilities, working through the equations to identify which futures are consistent with the laws of physics and which are ruled out. What emerges is not an endless catalogue of arbitrary outcomes, but a small, well-defined set of distinct fates, each one the logical consequence of a particular assumption about dark energy, matter, and the geometry of space. These scenarios are not idle guesses. They are derived from the same framework that successfully describes the expansion we observe, extended forward across the immense stretches of time that lie ahead. By narrowing the future down to a handful of clear alternatives, scientists have turned an impossibly vast question into something they can actually analyze, compare, and test against new data as it arrives. The first and oldest of these scenarios is the one that dominated cosmological thinking before dark energy was discovered. It depends entirely on the amount of matter and energy in the universe, and on whether that amount is sufficient to halt and reverse the expansion through gravity alone. Imagine the universe as a ball thrown upward from the surface of a planet. If the planet's gravity is strong enough relative to the speed of the throw, the ball will rise, slow, stop, and fall back. If the throw is fast enough to exceed the planet's escape velocity, the ball will climb forever, slowing but never returning. And at one precise dividing line, the ball will have exactly enough speed to keep rising forever while its velocity approaches zero, never quite falling back, but never fully escaping either. The universe faces an analogous set of options, governed by what cosmologists call its density. If the density of matter is high enough, gravity will eventually overcome the expansion, bring it to a halt, and pull everything back together. If the density is too low, the expansion continues without end. And at a critical density, the universe sits balanced on the knife's edge between these outcomes, expanding forever, but at an ever-decreasing rate. These three possibilities correspond to three different geometries of space, a connection that flows directly from Einstein's theory of gravity. In general relativity, matter and energy do not simply sit within space. They shape it, curving the fabric of space-time in ways that determine both how objects move and how the universe as a whole evolves. A universe with density above the critical value would be curved like the surface of a sphere, closing back on itself. And this closed geometry is tied to the fate of eventual collapse. A universe with density below the critical value would be curved the opposite way, like the surface of a saddle, an open geometry destined to expand forever. And a universe sitting exactly at the critical density would be flat, its geometry obeying the familiar rules of everyday space, where parallel lines never meet and the angles of a triangle add up as they do on a tabletop. Measuring the geometry of the universe, therefore became a way to measure its fate. And one of the great achievements of modern cosmology was determining, through precise observations of the early universe, that space is flat, or so close to flat that we cannot distinguish it from perfectly flat with current instruments. A flat universe, sitting at exactly the critical density, would, in the old picture, expand forever, while gradually slowing toward a halt it never quite reaches. But this clean picture was complicated by the discovery of dark energy, because dark energy adds a component that does not behave like matter and is not subject to the same gravitational braking. When cosmologists found that the universe is flat, and also discovered that it is accelerating, they realized that the flatness is achieved not by matter alone, but by the combination of matter, and dark energy together, summing to the critical density. The geometry is flat, but the dynamics are dominated by dark energy, and this changes everything about the projected ending. A flat universe driven by dark energy does not coast gently toward a slowing halt. It accelerates, and the geometry alone no longer tells the whole story of its fate. The future now depends on what dark energy does, and that introduces the additional scenarios that the simple matter density picture could never have predicted. This brings us to the modern landscape of cosmic endings, which can be organized around the behavior of dark energy over time. The most widely discussed scenario assumes that dark energy is a true cosmological constant, fixed in strength forever. Under this assumption, the universe expands faster and faster without limit. Galaxies recede beyond our reach, and the cosmos grows ever colder, darker, and more dilute as it approaches a state of maximum disorder. This is the scenario often called heat death, though the name is somewhat misleading since the end state is anything but hot. It describes a universe that has exhausted all the ordered energy capable of doing useful work, settling into a thin, cold, featureless expanse where nothing of consequence can happen. This is the default ending implied by our current best measurements, the fate the universe seems headed toward if dark energy remains exactly as it appears today. But if dark energy is not constant, other endings become possible. Suppose dark energy grows stronger over time, intensifying its push against the structures of the cosmos. In that case, the accelerating expansion would not merely carry galaxies apart, but would eventually overwhelm the forces that hold individual structures together. Galaxies would be torn from their clusters, stars ripped from their galaxies, planets pulled from their stars, and ultimately atoms themselves shredded as the expansion of space outpaced the bonds holding everything together. This violent ending is known as the Big Rip, and it represents the most dramatic possible consequence of a dark energy that escalates without bound. It is not the favored scenario based on current data, but it remains a live possibility precisely because we cannot yet rule out a dark energy that strengthens with time. At the opposite extreme lies the possibility that dark energy weakens or even reverses its sign, switching from a force that pushes space apart to one that pulls it together. If this were to happen, the acceleration would slow, stop, and reverse, and gravity would finally be able to reassert its ancient role. The expansion would give way to contraction, and the universe would begin to fall back in on itself, the great outward flow of galaxies reversing into an inward rush. Over immense spans of time, everything would draw closer together, the universe growing hotter and denser as it contracted, until it collapsed into a state resembling the conditions of its own birth. This scenario is the Big Crunch, the mirror image of the Big Bang, and it offers something the other endings do not: namely the tantalizing possibility that the collapse might not be truly final, but could instead set the stage for a new beginning. These scenarios, heat death through eternal acceleration, the big rip through escalating dark energy, and the big crunch through weakening or reversing dark energy, form the core of modern thinking about the cosmic future. Each is a serious proposal, grounded in physics, and consistent with some range of possible dark energy behaviors. Which one the universe will actually follow remains undetermined, because it hinges on properties of dark energy that we have not yet measured precisely enough to distinguish. The recent hints that dark energy might be evolving rather than constant have only sharpened the interest in these alternatives, because a dynamic dark energy could lead the universe down any of several paths that a fixed cosmological constant would forbid. The endings are not equally likely given what we know now, and the steady acceleration toward a cold, dilute future remains the most consistent with present observations. But the others have not been eliminated, and a sufficiently dynamic dark energy could yet steer the cosmos toward a tearing or a collapse. What unites all of these scenarios is that they describe processes unfolding across timescales so vast that ordinary human language struggles to convey them. We are not talking about millions or even billions of years, the kinds of durations we use to describe the lifetimes of stars or the age of the universe so far. We are talking about timescales that dwarf the current age of the cosmos by factors so large that the present moment, the entire history of the universe up to now, amounts to little more than the opening instant of a story still in its earliest scene. To understand how any of these endings actually arrives, we have to follow the universe forward through these enormous stretches of time, watching how the familiar features of the cosmos, the stars and galaxies and structures we take for granted, fade and transform and ultimately disappear. The first stage of that long journey involves something that sounds almost gentle compared to a rip or a crunch, but which represents the beginning of the end for the luminous universe we know. It begins with the slow exhaustion of the stars, the gradual dimming of the cosmic light, and the onset of a darkness that will only deepen from there. The most familiar feature of the night sky is also the most temporary. Stars seem permanent to us, fixed points that have shone since long before humanity existed, and will, we instinctively assume, continue shining long after we are gone. On human timescales, this assumption is harmless, but stretched across cosmic time, it is simply false. Stars are not eternal. They are engines that consume fuel, and like any engine running on a finite supply, they will eventually run dry. The slow exhaustion of the stars is the first great chapter in the deep future of the universe, the opening movement of an ending that will unfold across spans of time so long that the entire history of the cosmos up to the present represents only the briefest preface. To understand how the lights go out, we first have to understand how they were lit and why their burning cannot last forever. A star is a balance between two opposing forces, and its entire life is the story of maintaining that balance. On one side is gravity, the relentless inward pull of the star's own enormous mass, which constantly tries to crush the star into a smaller and smaller volume. On the other side is the outward pressure generated by nuclear fusion in the star's core, where the crushing heat and density force atomic nuclei to merge together, releasing energy in the process. This energy pushes outward, holding the star up against its own gravity and keeping it stable. As long as the fusion continues, the balance holds and the star shines steadily. converting its core of light elements into heavier ones and pouring the released energy out into space as light and heat. Our own sun has been performing this balancing act for billions of years and will continue for billions more, fusing hydrogen into helium at a rate that has kept it remarkably stable across the entire span of life on Earth. But the fuel is finite, and when it begins to run low, the balance breaks down. The way a star dies depends almost entirely on its mass, and this mass dependence shapes the entire future evolution of the cosmic light. Massive stars, those many times heavier than the sun, burn through their fuel with astonishing speed, blazing brilliantly but briefly before exhausting their cores and collapsing in catastrophic explosions that scatter their material across space and leave behind dense remnants. These massive stars are rare, and their lives are short, measured in mere millions of years rather than billions. Smaller stars, by contrast, burn their fuel slowly and frugally, eking out existences that stretch across enormous spans of time. The smallest and most common stars, the dim red dwarfs that make up the majority of all stars in the universe, are so economical with their fuel that a single one can continue fusing hydrogen for trillions of years, far longer than the current age of the universe. These modest, long-lived stars are the ones that will keep the cosmos dimly lit long after the brighter, more massive stars have burned out and vanished. To see how the light fades, we have to follow the supply of fresh stellar fuel, because new stars are constantly being born even as old ones die. Stars form from clouds of gas and dust that collapse under their own gravity, igniting fusion when the core grows hot and dense enough. The universe is still actively forming stars today, drawing on vast reservoirs of gas spread throughout the galaxies. But this gas is being consumed faster than it is replenished, and the rate of star formation across the cosmos has been declining for billions of years. The peak of cosmic star birth lies in the distant past, when the universe was young and rich with raw material. Since then, galaxies have been gradually using up their gas, locking it away in stars that will eventually die, without returning all of their material to the interstellar medium. Each generation of stars consumes some of the available gas permanently, sequestering it in dead remnants that no longer contribute to forming new stars. Over immense spans of time, this process drains the cosmic fuel supply, and as the gas runs out, fewer and fewer new stars will form to replace those that die. There will come a time, far in the future, when the last clouds of star-forming gas are finally exhausted, when no new stars can be born because there is nothing left to build them from. After that point, the universe will contain only the stars that already exist, a finite and dwindling population with no possibility of renewal. From that moment, the cosmic light can only fade. The most massive remaining stars will die first, their brief lives ending in collapse and explosion. The sun-like stars will follow, swelling into bloated giants in their final phases before shedding their outer layers and settling into slowly cooling embers. And the long-lived red dwarfs will persist for an extraordinarily long time, burning their meager fuel with such patience that they will be the last stars shining in an otherwise darkening cosmos. But even they cannot last forever. Eventually, one by one, they too will exhaust their hydrogen and fade. And when the final red dwarf flickers out, the era of starlight will come to an end. The universe will have entered a new phase, one without the steady glow of fusion that has illuminated it since the first stars ignited. It is worth pausing to consider just how long this process takes, because the timescales involved are difficult to grasp. The brightest, most massive stars live and die in spans short enough that many generations of them have already come and gone since the universe began. Stars like the Sun live for roughly 10 billion years, comparable to the current age of the universe, which is why the Sun is now in the middle of its life rather than near its end. But the red dwarfs operate on a completely different scale. A small red dwarf can continue fusing hydrogen for many trillions of years, a duration that exceeds the present age of the universe by a factor of hundreds or even thousands. This means that the era of starlight, the period during which stars are actively shining across the cosmos, will extend far beyond anything we normally imagine when we think about the future. We are, in fact, living near the very beginning of this stellar era, in the bright early dawn of a cosmic day that will continue for an almost incomprehensibly long time before the light finally begins to fail in earnest. As the stars age and the gas runs out, the appearance of the universe will change profoundly, though the change will be so gradual that it would be imperceptible on any human timescale. The sky will slowly empty of bright young stars, growing dominated by the dim red glow of the long-lived dwarfs and the fading embers of dead stars. Galaxies that once blazed with the brilliant blue light of massive young stars will redden and dim as those bright stars die and are not replaced. The overall light of the cosmos will shift toward the red end of the spectrum and then toward the infrared, growing fainter and cooler as the stellar population ages. Eventually, the visible light will fade almost entirely, leaving only the faintest residual glow from the coolest, dimmest remnants. An observer in this far future, if any could exist, would look out on a sky almost entirely dark, the brilliant cosmos of our era, reduced to scattered, feeble embers, slowly winking out. This cooling and dimming is not a sudden catastrophe, but a long, inexorable decline, the natural consequence of a finite fuel supply being consumed over time. There is nothing violent about it in the way that an explosion or a collapse is violent. It is simply the universe running down, exhausting the resources that made it bright. And yet this gentle fading represents a fundamental and irreversible transition. Once the gas is gone and the stars have died, there is no mechanism in the standard picture that can relight them. The light, once extinguished, stays extinguished. The universe does not have a way to gather fresh fuel and begin the cycle of star formation anew, at least not under the conditions we expect to prevail. The era of starlight, for all its grandeur and duration, is a one-time event in the life of the cosmos, a phase that begins, flourishes, and ends, never to return. But the end of starlight does not mean the end of everything. When the last star fades, the universe will not be empty. It will be populated by the corpses of the stars that once shone, the dense remnants left behind when fusion ceased. These objects, the cooling cores of dead stars, will drift through the darkness, no longer generating light through fusion, but still possessing mass, structure, and in some cases enormous density. They will be the dominant inhabitants of the post-stellar universe, the residents of a cosmos that has moved beyond the age of starlight into something colder and stranger. What these remnants are, how they behave, and what eventually becomes of them is the next chapter in the story, because the fading of the stars only sets the stage for what follows. The darkness that descends when the last star dies is not the final state of the universe, but merely the beginning of a far longer era. One ruled not by living stars, but by their cold and lingering remains. These remnants come in several distinct varieties, each the corpse of a different kind of star, and together they will form the population of a universe that has outlived its own starlight. The most common of these stellar corpses is the white dwarf, the fate that awaits the great majority of stars, including our own sun. When a sun-like star exhausts the hydrogen in its core, it does not simply switch off. It goes through a series of final contortions, swelling into an enormous red giant as it begins fusing heavier elements, then casting off its bloated outer layers into space in a slow, expanding shell of gas. What remains when this shedding is complete is the star's exposed core, a sphere of extraordinarily dense material, roughly the size of a planet, but containing a substantial fraction of the original star's mass. This is a white dwarf, and it is one of the strangest objects in the cosmos. A single spoonful of its material would weigh as much as a large vehicle, because the matter inside is compressed to a degree that ordinary experience cannot prepare us for. The white dwarf no longer generates energy through fusion. It simply sits there, retaining the heat left over from its days as a living star, and radiating that heat slowly away into the surrounding darkness. A freshly formed white dwarf is intensely hot, glowing white from the residual heat of its former life, which is how it earned its name. But with no fusion to replenish that heat, it can only cool, gradually radiating its warmth into space over enormous spans of time. As it cools, it dims and reddens, fading from white through yellow and orange toward red, and eventually toward darkness altogether. The timescale for this cooling is immense. A white dwarf will continue glowing faintly for billions upon billions of years, far longer than the current age of the universe, before it finally fades into a cold, dark object known as a black dwarf. In fact, the cooling time is so long that the universe is not yet old enough to contain any black dwarfs at all. Every white dwarf that has ever formed is still warm enough to glow, however faintly. The black dwarf is a creature of the deep future, a remnant so old that it has shed essentially all of its heat and become a cold, dense sphere of dead matter, dark and inert, drifting through a darkening cosmos. In the far future, after the era of starlight ends, these black dwarfs will be among the most numerous large objects in the universe, the cooled and silent corpses of stars that once shone. Heavier stars leave behind denser and stranger remnants. A star considerably more massive than the sun does not end its life quietly. When such a star exhausts its fuel, its core collapses with tremendous violence, and the outer layers are blown away in a supernova, one of the most energetic events in the cosmos. What remains depends on how much mass is left behind. In many cases, the collapsing core is compressed far beyond the density of a white dwarf, crushing protons and electrons together until the entire core becomes a single, almost unimaginably dense ball of neutrons. This is a neutron star, an object that packs more mass than the sun into a sphere only a few miles across. The density inside a neutron star is so extreme that a sugar cube of its material would weigh as much as a mountain. Neutron stars often spin rapidly and possess intense magnetic fields, and in their youth they can be observed as pulsars, sweeping beams of radiation across space like cosmic lighthouses. But like white dwarfs, neutron stars generate no new energy through fusion. They are remnants, slowly cooling and spinning down over time, and in the deep future, They too will fade into cold, dark, dense objects, the silent survivors of stars that died in fire. For the most massive stars of all, even the neutron star stage cannot hold. When the collapsing core exceeds a certain mass, no known force can resist the inward pull of gravity, and the core continues to collapse without limit, crushing itself into a region of such extreme density that not even light can escape its gravitational grip. This is a black hole, an object so dense that it warps space-time into a configuration from which nothing can return. The black hole represents the ultimate triumph of gravity over all the forces that normally support matter against collapse. Where a white dwarf is held up by the resistance of its tightly packed electrons, and a neutron star by the resistance of its neutrons, a black hole has no such support. Gravity has won completely, compressing the matter into a state we cannot fully describe with current physics and surrounding it with a boundary, the event horizon, beyond which the interior is forever hidden from the outside universe. Black holes formed from collapsing stars will be among the longest-lived structures in the cosmos, persisting long after the white dwarfs and neutron stars have faded, and they will come to play a dominant role in the far future of the universe. So the post-stellar universe, the cosmos that exists after the last star has died, will be populated by this menagerie of remnants. There will be black dwarfs, the cold corpses of sun-like stars, drifting in enormous numbers through the darkness. There will be neutron stars, dense and silent, slowly cooling toward their own final darkness. And there will be black holes, ranging from the modest ones formed by collapsing stars to the supermassive giants that lurk at the centers of galaxies, containing the mass of millions or billions of suns. Scattered among these major remnants will be the smaller debris of the cosmos, planets that have lost their stars, asteroids and comets, clouds of cold gas too sparse to form new stars, and the occasional rogue object wandering through interstellar space. This will be a cold and dark universe, lit by nothing but the faintest residual glow of cooling remnants and the rare flashes of occasional collisions, a place utterly transformed from the bright, active cosmos of our own era. It is important to understand that this transformation does not happen all at once, and that the universe passes through distinct phases on its way to this state. For an enormous span of time, the era of starlight continues, with stars being born, living and dying in a great ongoing cycle. As the gas runs out, the cycle slows, and the population of living stars dwindles while the population of remnants grows. Eventually, a crossover occurs, when the remnants come to outnumber and outweigh the living stars, and the character of the universe shifts decisively from a cosmos of fusion-powered light to a cosmos of cold, dead matter. This crossover marks the true beginning of the post-stellar era, sometimes called the degenerate era, after the peculiar state of matter found in white dwarfs and neutron stars, which physicists describe as degenerate matter because of the strange quantum rules that govern its behavior under such extreme compression. In this degenerate era, the dominant objects are the dense remnants, and the universe is sustained not by fusion, but by the slow processes that govern these cold corpses over the immense stretches of time still to come. Even in this dark and quiet era, the universe is not entirely static. Occasional events still occur, though they grow rarer as time passes. Remnants sometimes collide or merge, releasing bursts of energy and radiation in brief flashes against the prevailing darkness. Black dwarfs may very rarely encounter one another and combine. black holes continue to draw in whatever matter strays too close, growing slowly as they consume the scattered debris of the cosmos. And gravitational interactions between objects gradually rearrange the contents of galaxies, flinging some objects outward into the empty space between galaxies, while drawing others inward toward the central black holes. These processes are slow, almost imperceptibly so, but across the vast timescales of the degenerate era, they steadily reshape the universe, breaking down the structures that formed during the Age of Starlight and setting the stage for the next great transition. For the galaxies themselves, which have held their stars and remnants together through the gravitational glue that binds them, are not permanent either. Over time, the very structures that organize matter into galaxies will come undone, scattering their contents and dismantling the cosmic architecture that has persisted since the early universe. How that dismantling unfolds and what it leaves behind is the next stage in the long unwinding of the cosmos. Galaxies appear to us as the grand, stable structures of the universe, vast pinwheels and spheres of stars that seem as fixed and permanent as anything could be. The galaxy we inhabit, with its hundreds of billions of stars arranged in a sweeping spiral, has maintained its general form for billions of years and looks, from our vantage point, like a settled and enduring feature of the cosmos. But this appearance of permanence is another illusion of timescale. Galaxies are not eternal structures. They are bound collections of stars and remnants held together by gravity, and over sufficiently long spans of time, the gravitational interactions among their countless members will slowly tear them apart. The decay of galaxies is the next stage in the long unwinding of the cosmos, a process that operates through the patient accumulation of small gravitational nudges across timescales that dwarf even the long lives of the stars. To understand how a galaxy comes apart, we have to think about what holds it together and how that binding can fail. A galaxy is a swarm of objects, each one moving under the combined gravitational influence of all the others. The stars do not orbit in neat, isolated paths like planets around a single sun. Instead, each star follows a complex trajectory, shaped by the ever-shifting pull of its billions of neighbors. Most of the time, these interactions are gentle and distant, with stars passing one another at great distances and exchanging only slight gravitational tugs. But occasionally, two objects pass close enough to exchange a significant amount of energy and momentum in what amounts to a gravitational encounter. In such an encounter, one object can gain speed while the other loses it, much like two balls exchanging momentum in a collision, except that the objects need never actually touch. The gravitational interaction alone is enough to redistribute energy between them. Over enormous spans of time, these encounters have a cumulative effect that gradually breaks down the structure of the galaxy. The process is similar to what happens in any system, where particles repeatedly exchange energy through random interactions. Some objects, through a series of fortunate encounters, gain enough speed to escape the galaxy entirely, flung outward into the empty space between galaxies, never to return. Each time an object is ejected in this way, it carries off some of the galaxy's energy, and the remaining objects must settle into a more tightly bound configuration to compensate. This means that as the galaxy loses members to ejection, its core grows more compact and more tightly bound, while the outer regions are steadily stripped away. The galaxy slowly evaporates from the outside in, shedding stars and remnants into intergalactic space, while its central region contracts. This process, known as gravitational evaporation, will eventually dismantle the galaxy as a coherent structure, scattering most of its contents across the void and concentrating the remainder in an increasingly dense core. But evaporation is only part of the story, because at the heart of nearly every large galaxy lies a supermassive black hole, an object containing the mass of millions or billions of suns. These central black holes play a crucial role in the fate of their host galaxies. As stars and remnants follow their orbits, gravitational interactions occasionally send some of them on trajectories that carry them close to the central black hole. Objects that venture too close are captured, drawn into the black hole and added to its mass. Over time, this slow accretion allows the central black hole to grow, consuming a fraction of the galaxy's contents, while the rest are ejected through evaporation. The competition between these two processes, evaporation flinging objects outward and accretion drawing them inward, determines the ultimate disposition of the galaxy's matter. Some fraction escapes into the void, and some fraction is swallowed by the central black hole. But in either case, the galaxy as a recognizable structure ceases to exist. What was once a vast, organized swirl of hundreds of billions of stars becomes either scattered debris drifting through intergalactic space, or additional mass locked away inside a growing black hole. The timescale for this galactic dismantling is staggering, far longer even than the lifetimes of the longest-lived stars. Gravitational evaporation operates through the slow accumulation of rare close encounters. And because such encounters are infrequent, the process requires spans of time that exceed the stellar era by enormous factors. By the time galaxies have substantially evaporated, the universe will be unimaginably old, the era of starlight will be a distant memory, and the cosmos will consist almost entirely of cold remnants and black holes. The dismantling of galaxies is thus a process of the deep, degenerate era, unfolding long after the last star has died, gradually erasing the large-scale structure that organized matter throughout the bright history of the universe. The cosmic web of galaxies and clusters, the grand architecture that astronomers map across the observable universe today, will slowly dissolve, its components either cast into the growing emptiness or absorbed into the dark, dense objects that increasingly dominate the cosmos. There is another factor that accelerates the isolation of galaxies, and it brings us back to dark energy and the accelerating expansion. Even as individual galaxies evaporate internally, the space between galaxies is stretching at an ever-increasing rate. Galaxies that are not gravitationally bound to one another are being carried apart by the expansion, and as the acceleration continues, they recede from one another faster and faster. From the perspective of any one galaxy, the others are retreating into the distance, their light stretched and dimmed by the expansion, until they fade from view entirely. Eventually, if dark energy continues as a constant, every galaxy beyond our own local gravitationally bound group will disappear beyond the horizon of observability, carried away so rapidly by the expansion that their light can no longer reach us. An observer in the far future, situated in what remains of our galaxy and its bound companions, would look out on a cosmos that appears almost entirely empty, with no other galaxies visible anywhere in the sky. The rich, galaxy-filled universe we observe today would have vanished from view, leaving only the local island of bound matter adrift in an apparently empty void. This combination of internal evaporation and external isolation means that galaxies face a double dismantling. Internally, they come apart as their stars, and remnants are ejected or consumed. Externally, they are separated from one another by the relentless expansion of space, each one increasingly alone in an enlarging void. The result is a universe in which the structures that once organized matter into a vast cosmic web have broken down completely, leaving behind isolated black holes, scattered remnants, and the thinning debris of what were once magnificent galaxies. The cosmic neighborhoods that astronomers study today, the clusters and superclusters and filaments that span the observable universe, will have dissolved into disconnected fragments, each fragment cut off from the others by an expanse of space that grows wider and emptier with every passing moment. It is worth dwelling on what this means for the possibility of knowledge in the far future. We are fortunate to live at a time when the universe is rich with observable structure, when the light of distant galaxies still reaches us and reveals the history and extent of the cosmos. By studying that light, we have been able to reconstruct the expansion, discover dark energy, and map the large-scale architecture of the universe. But this window of observability is temporary. As galaxies recede beyond the horizon and the cosmos empties of visible structure, the evidence that allowed us to understand the universe will gradually disappear. A civilization arising in the far future, after the galaxies have isolated and the cosmic web has dissolved, would look out on a nearly empty sky and might have no way to discover that the universe was once filled with galaxies, that it had expanded from a hot, dense state, or that dark energy was driving everything apart. The very expansion that shapes the cosmic future also erases the clues to its past. We occupy a privileged moment, a window during which the universe's history is still legible, and that window is slowly closing. As galaxies evaporate and isolate, the matter they contained does not simply vanish. The ejected stars and remnants drift into the growing void, while the rest is drawn into the central black holes, which continue to grow as they consume the material that falls within their reach. With the dismantling of galaxies, the universe enters a phase increasingly dominated by these black holes, the dark, dense objects that have been accumulating mass throughout cosmic history, and that will outlast nearly everything else. But before we follow the cosmos into that black hole-dominated era, there is a question we have so far left aside, a question about the fate of ordinary matter itself. We have assumed that the remnants, the black dwarfs and neutron stars and scattered debris, will persist essentially unchanged for as long as they avoid being ejected or consumed. But there is reason to suspect that ordinary matter may not be permanent at all, that the very particles from which everything is built might themselves slowly decay, dissolving the remnants from within and erasing the last solid structures of the cosmos. Whether matter is truly stable, or whether it carries within it the seeds of its own dissolution, is a question that bears directly on what the far future holds. The stability of matter is something we take entirely for granted, and with good reason. The objects around us, the materials that make up our bodies and our world, appear to persist indefinitely without any sign of spontaneous disintegration. A block of iron left undisturbed does not slowly evaporate into nothing. The atoms that compose it seem to last forever, and our everyday experience offers no hint that ordinary matter might be anything other than permanent. At the heart of this apparent permanence is a particle called the proton, one of the basic building blocks of atomic nuclei. Every atom of ordinary matter contains protons in its nucleus, and the proton has long been considered one of the most stable entities in nature. If protons are truly stable, lasting forever without decaying, then the remnants of the far future, the black dwarfs and neutron stars and scattered debris, could persist essentially unchanged for as long as they avoid being consumed by black holes or ejected into the void. But if protons are not perfectly stable, if they very slowly decay over time, then the entire picture of the far future changes, because the solid matter of the cosmos would be dissolving from within. The question of whether protons decay arises from attempts to unify the fundamental forces of nature into a single coherent framework. Physicists have long sought a deeper theory that would describe the forces governing the universe as different aspects of one underlying force, a goal that has driven much of theoretical physics for decades. Some of the proposed theories that attempt this unification predict that the proton, far from being perfectly stable, should very occasionally decay, transforming into lighter particles and releasing energy in the process. The predicted rate of this decay is extraordinarily slow, so slow that an individual proton would, on average, survive for a span of time vastly longer than the current age of the universe before decaying. This is why proton decay, if it occurs at all, has never been a concern in everyday life, or even in the lifetime of the universe so far. The timescales involved are so immense that only across the deep future of the cosmos would proton decay have a noticeable effect. Despite the predictions of these unifying theories, proton decay has never actually been observed. Physicists have searched for it diligently, building enormous detectors deep underground, where they monitor vast quantities of water or other materials, watching for the telltale signature of even a single proton decaying among the astronomical number of protons contained in the detector. The logic is straightforward. Although any individual proton is overwhelmingly unlikely to decay within a human lifetime, a sufficiently large collection of protons might produce a few decays that could be detected, given enough protons and enough patience. So far, these searches have come up empty. No confirmed instance of proton decay has ever been recorded, and the absence of detected decays has allowed physicists to establish that if protons do decay, their average lifetime must be longer than a certain enormous threshold, a span of time that already exceeds the simplest predictions of some unification theories. This null result has ruled out some of the proposed theories and constrained others, but it has not settled the fundamental question. Protons might decay on a timescale longer than current experiments can probe, or they might be perfectly stable. We simply do not yet know. This uncertainty matters enormously for the far future, because the two possibilities lead to very different fates for ordinary matter. Suppose protons do decay, even if only on a timescale far longer than the current age of the universe. In that case, every object made of ordinary matter would eventually dissolve. The black dwarfs, those cold corpses of sun-like stars, would slowly evaporate as their protons decayed one by one, gradually losing mass and structure until they disintegrated entirely. The neutron stars, the planets, the scattered debris, all of it would crumble over time as the protons within them decayed into lighter particles. The decay would be agonizingly slow by any human standard, with each object taking an almost incomprehensibly long time to fully dissolve. But across the vast stretches of the far future, even the most durable remnants would eventually come apart. The matter that survived the death of the stars and the dismantling of the galaxies would, in this scenario, ultimately succumb to the decay of its own most basic constituents, leaving behind only the lighter particles into which the protons transformed. If proton decay proceeds in this way, the universe of the far future would gradually empty of solid matter. The cold remnants that populate the degenerate era would not last forever, but would slowly fade away, their substance converted into radiation and lighter particles that disperse through the expanding void. The cosmos would transition from a universe of dense remnants to a universe of diffuse particles and radiation, the last solid objects having dissolved into the thin background. This would represent a profound transformation, the final dissolution of ordinary matter as a meaningful component of the universe. The atoms that built stars and planets and living things would have run their course, their fundamental particles having decayed into a sparse haze, spreading through an ever-growing emptiness. In this picture, the degenerate era of remnants is itself only a phase, destined to give way to an era in which ordinary matter has all but vanished. But suppose instead that protons are perfectly stable, that they never decay at all. In that case, the remnants would not dissolve through proton decay, and ordinary matter would persist far longer, limited only by other processes. The black dwarfs and neutron stars would endure, cold and dark but intact, for spans of time even longer than the proton decay scenario would allow. Yet even in this case, the remnants would not last forever, because other, even slower processes would eventually come into play. Over timescales so long that they strain the very meaning of the word, quantum mechanical effects could slowly transform the matter within the remnants, gradually converting it through extraordinarily rare processes into more stable configurations. And ultimately, the remnants might collapse into black holes through the slow, patient action of quantum tunneling. These timescales are so vast that they dwarf even the already enormous spans associated with proton decay, representing durations so long that ordinary numerical description loses all intuitive meaning. But the principle remains. Whether through proton decay or through these even slower quantum processes, the solid matter of the cosmos is not truly permanent. Given enough time, and the far future offers time without apparent limit, the remnants will come apart. The fate of ordinary matter therefore hinges on physics we have not yet fully established, on questions about the deep structure of the fundamental forces and the stability of the particles that build everything we know. The ongoing experiments deep underground, watching patiently for a single proton to decay, are in a real sense probing the far future of the universe, testing whether the matter around us carries within it the seeds of its own eventual dissolution. A confirmed detection of proton decay would not only revolutionize our understanding of fundamental physics, but would also settle the question of how the remnants meet their end, confirming that ordinary matter is destined to dissolve over the immense spans of the far future. The continued absence of such a detection, by contrast, pushes the proton lifetime ever longer and keeps open the possibility that ordinary matter is more durable than some theories suggest, though never truly eternal. What emerges from all of this is a picture in which ordinary matter, for all its apparent solidity and permanence, is ultimately a transient feature of the cosmos. The stars die, the galaxies dismantle, and the remnants themselves eventually dissolve, whether through the decay of their constituent protons or through even slower quantum processes operating across almost unthinkable spans of time. In every version of the story, the solid, substantial universe of our era gives way to something thinner and emptier, a cosmos increasingly dominated not by matter, but by the objects that can outlast it. And among all the structures of the universe, there is one class of object that proves more durable than any remnant, more persistent than any star, surviving long after ordinary matter has dissolved. These are the black holes, the dark, dense survivors that come to rule the cosmos in its deep old age, dominating an era that stretches across timescales, beside which even the dissolution of matter seems brief. How black holes come to dominate, and what eventually becomes of them, is the next chapter in the unwinding of the universe. As ordinary matter dissolves and the remnants fade, the black holes remain. They are the great survivors of the cosmos, the objects that outlast nearly everything else. And in the deep future, they come to dominate the universe to such an extent that this period is sometimes called the black hole era. To understand why black holes inherit the cosmos, we have to appreciate what they are and why they prove so much more durable than any other structure. A black hole is a region of space where gravity has become so intense that nothing, not even light, can escape from within a certain boundary. It forms when matter is compressed beyond the point where any known force can resist further collapse, crushing it into a state so dense that it warps the surrounding space-time into a configuration from which there is no return. The boundary of this region, the event horizon, marks the point of no return. Anything that crosses it is lost to the outside universe forever, drawn inexorably toward the center, while the outside world can never again receive any signal from within. Black holes come in a wide range of sizes, and this range matters for understanding their role in the far future. The smallest black holes that form in the present universe are the stellar mass black holes, created when the most massive stars collapse at the ends of their lives. These contain several times the mass of the Sun compressed into a region only a few miles across. Far larger are the supermassive black holes that lurk at the centers of galaxies, containing the mass of millions or even billions of suns. These giants grew over cosmic history by consuming gas, stars, and smaller black holes, accumulating their enormous masses through long ages of accretion and merger. As galaxies dismantle and their contents are drawn inward, these central black holes continue to grow, swallowing the remnants and debris that fall within their reach. In the far future, after galaxies have evaporated and ordinary matter has begun to dissolve, the black holes remain as the largest and most massive structures in the cosmos, dark and dense, holding within them the swallowed substance of countless stars. For an enormous span of time, the black hole era is a period of profound darkness and quiet. The stars are long dead, the galaxies long dismantled, and ordinary matter has largely dissolved. The black holes drift through an immense and nearly empty void, each one isolated by the relentless expansion of space, surrounded by almost nothing. Occasionally, a stray particle or a wandering remnant might fall into one of them, releasing a faint flicker of energy as it crosses the event horizon. But such events grow ever rarer as the universe empties out. For the most part, the black holes simply persist, dark and silent, in a cosmos that has grown colder, emptier, and more featureless than anything in its bright early history. If one imagines the universe as having a lifespan, the black hole era represents its deep old age, a time long after the vigorous activity of youth has faded, when little remains but the slow, patient endurance of the most durable structures. It would be natural to assume that black holes, having consumed so much and resisted the dissolution that claims ordinary matter, are truly permanent, that they will persist unchanged forever as the final, eternal residents of the cosmos. For most of the history of physics, this is exactly what was believed. A black hole was thought to be a perfect trap, a one-way door through which matter and energy could enter, but from which nothing could ever emerge. By this understanding, black holes could only grow or stay the same, never shrink, and once formed, they would last for all eternity. But this understanding turned out to be incomplete, and the discovery that overturned it ranks among the most profound insights in modern physics. It emerged from an unexpected marriage of two great theories that had previously seemed to have little to do with one another. The theory of gravity that describes black holes, and the theory of quantum mechanics that describes the behavior of matter and energy at the smallest scales. When these two frameworks were brought together at the boundary of a black hole, they revealed something that no one had anticipated. Black holes are not perfectly black after all. They slowly leak energy, and over immense spans of time, they evaporate. This realization transformed black holes from eternal objects into temporary ones, albeit temporary on timescales that defy comprehension. The leaking of energy from a black hole is an extraordinarily slow process, especially for the large black holes that dominate the far future. A massive black hole leaks energy so gradually that it would take spans of time vastly exceeding all the eras that came before: the stellar era, the degenerate era, and the long reign of the black holes themselves, for it to lose a significant fraction of its mass. The supermassive black holes that anchored the centers of galaxies would persist for almost inconceivable durations, slowly leaking energy into the surrounding void, shrinking by imperceptible amounts across spans of time, beside which the entire previous history of the universe is the briefest flicker. But shrink they do, and given the limitless time available in the far future, even this glacial process eventually runs its course. The black holes, the great survivors of the cosmos, are themselves on a path toward dissolution, leaking away their substance until nothing remains. The mechanism by which black holes leak energy is subtle and deeply counterintuitive, rooted in the strange behavior of the quantum vacuum near the event horizon. To grasp it, we have to return to the idea, discussed earlier in connection with dark energy, that empty space is not truly empty, but seethes with quantum activity, with pairs of particles constantly flickering into existence and annihilating one another. Near the boundary of a black hole, this quantum activity interacts with the intense gravity in a way that allows energy to escape. The process effectively converts a tiny portion of the black hole's mass into a faint stream of radiation that flows away into space. Because the black hole loses mass in this way, it slowly shrinks, and as it shrinks, the process gradually accelerates. The details of this mechanism reveal a deep connection between gravity, quantum mechanics, and the nature of heat and disorder, a connection that physicists are still working to fully understand. But the essential consequence is clear. Black holes are not eternal. They evaporate, releasing their substance back into the cosmos as a thin trickle of energy over spans of time so long that they stretch the limits of meaningful description. The way this evaporation proceeds is itself remarkable because it accelerates as it goes. A large black hole leaks energy with extreme slowness But as it loses mass and shrinks, the leaking grows faster. The smaller a black hole becomes, the more rapidly it radiates, so that the process speeds up over time. After spending almost the entire span of its existence shrinking imperceptibly slowly, a black hole in its final stages would dwindle ever faster, its remaining mass radiating away in an accelerating cascade. The very end of a black hole's life, after an existence stretching across spans of time that defy comprehension, would come relatively quickly, a final burst of energy as the last of its mass is released. The great durable survivors of the cosmos, the objects that outlasted the stars and the galaxies and ordinary matter itself, would end not with a slow fade into nothing, but with a comparatively swift release of their final substance. The last black holes vanishing in bursts that mark the end of the era they once dominated. When the last black hole has evaporated, the universe will have lost its final large-scale structures. The stars died long before, the galaxies dismantled, ordinary matter dissolved, and now even the black holes, the most durable objects the cosmos ever produced, have leaked away into radiation. What remains is a universe almost entirely devoid of structure, filled with nothing but a thin, cold haze of particles and radiation spreading through an enormous and ever-expanding void. This is the deepest old age of the cosmos, a state reached only after spans of time so immense that all the previous eras combined represent a vanishingly small fraction of the whole. But the mechanism by which black holes evaporate, this slow leaking of energy from the event horizon, deserves closer examination because it represents one of the most profound discoveries in all of physics, a faint whisper of radiation that revealed black holes to be mortal after all. Understanding how this whisper emerges from the marriage of gravity and quantum mechanics opens a window onto some of the deepest questions about the nature of reality itself. The discovery that black holes radiate energy emerged in the 1970s from the work of the physicist Stephen Hawking, and it represented a genuine surprise, a result so unexpected that even its discoverer was initially reluctant to believe it. Hawking had been studying the behavior of quantum fields near the event horizons of black holes, applying the rules of quantum mechanics to the curved space-time that gravity produces around these objects. What he found contradicted the prevailing wisdom completely. According to his calculations, black holes were not perfectly black. They should emit a faint glow of radiation, a steady trickle of particles flowing outward from the vicinity of the event horizon. This radiation, now called Hawking radiation, carries energy away from the black hole, and because energy and mass are equivalent, the black hole must lose mass as it radiates. Over time, this loss of mass causes the black hole to shrink and ultimately to evaporate entirely. The implication was revolutionary. Black holes, long thought to be eternal, were in fact mortal, destined to leak away their substance and disappear given sufficient time. The mechanism behind Hawking radiation is rooted in the quantum nature of empty space, and understanding it requires setting aside the intuition that a vacuum is simply nothing. As discussed earlier, the vacuum of space is not truly empty, but is filled with quantum activity, with pairs of particles and antiparticles constantly appearing and disappearing in fleeting bursts. These pairs ordinarily annihilate one another almost immediately, leaving no lasting trace. And under normal circumstances, their fleeting existence has no observable consequence beyond subtle effects measurable in the laboratory. But near the event horizon of a black hole, the situation changes. The intense gravity at the boundary can separate a pair before they have a chance to annihilate, with one member falling into the black hole while the other escapes outward. The escaping particle carries energy away from the black hole, appearing to a distant observer as part of the steady glow of Hawking radiation. Meanwhile, to balance the energy budget, the black hole effectively loses a corresponding amount of mass. Through this process, repeated countless times across the event horizon, the black hole slowly bleeds away its substance. This description, while widely used, is a simplification of a deeper and more subtle reality, and physicists are careful to note that the picture of particle pairs at the horizon is more of a useful analogy than a complete account. The full explanation involves intricate mathematics describing how quantum fields behave in the curved space-time around a black hole, and it reveals that the radiation arises from a fundamental mismatch between how empty space is defined near the horizon and how it is defined far away. What an observer far from the black hole perceives as a glow of outgoing particles is intimately connected to the way the black hole's gravity distorts the very notion of the vacuum. Despite the complexity of the full treatment, the essential conclusion is robust and has been confirmed through multiple independent lines of theoretical reasoning. Black holes radiate, they lose mass, and they eventually evaporate. The discovery united gravity and quantum mechanics in a way that had never been achieved before, and it continues to guide physicists searching for a deeper theory that would fully reconcile these two great frameworks. One of the most striking features of Hawking radiation is how it depends on the mass of the black hole, a relationship that runs counter to ordinary intuition. For most objects, larger means hotter and more energetic. But for black holes, the opposite is true. The smaller a black hole, the hotter it is, and the more intensely it radiates. A small black hole has a high temperature and leaks energy rapidly, while a large black hole has an extraordinarily low temperature and radiates with almost imperceptible slowness. The supermassive black holes at the centers of galaxies are so cold that their temperature is a tiny fraction of a degree above the lowest possible temperature, and they radiate so feebly that the process is utterly negligible in the present universe. In fact, these large black holes are currently colder than the faint background radiation that fills the cosmos, the leftover glow of the early universe, which means they are actually absorbing more energy from their surroundings than they emit. Only in the far future, after the background radiation has cooled below the temperature of the black holes, will the black holes begin to lose mass on balance and start their long evaporation. This temperature dependence has a dramatic consequence for how black holes meet their ends. Because smaller black holes radiate more intensely, the evaporation process accelerates as a black hole shrinks. A black hole spends the overwhelming majority of its existence as a large, cold object leaking energy with glacial slowness. But as it gradually loses mass, it grows hotter and radiates faster, and this speeds its further loss of mass, which makes it hotter still. The process feeds on itself, accelerating toward the end. In the final stages of its life, a black hole that has spent almost unimaginable spans of time shrinking imperceptibly would dwindle with increasing rapidity, its temperature soaring as its mass plummeted until the last of its substance was released in a final, relatively brief burst of energy. After an existence stretching across spans of time that dwarf all previous cosmic eras, a black hole would end its life in a comparatively swift flash, the accumulated mass of what might once have been a giant star or even a galactic core radiating away in the closing moments of its long evaporation. The timescales involved in black hole evaporation are almost beyond comprehension, varying enormously with the mass of the black hole. A black hole with the mass of a star would take a span of time vastly exceeding the current age of the universe to evaporate, a duration so long that the entire history of the cosmos so far would be an insignificant fraction of it. The supermassive black holes, containing the mass of millions or billions of suns, would take spans of time longer still, durations so immense that ordinary numerical description fails to convey their scale. These are the longest-lived structures the universe will ever produce, persisting through the deep black hole era and slowly leaking away their substance across spans of time, beside which even the dissolution of ordinary matter seems quick. The evaporation of the last and largest black holes marks one of the final major events in the history of the cosmos, the disappearance of the universe's most durable structures, and the transition into a state of near total emptiness. There is a profound puzzle embedded in the process of black hole evaporation, one that has occupied physicists for decades and remains a subject of intense debate. When matter falls into a black hole, it carries with it information about its precise configuration, the detailed arrangement of its particles, and their properties. According to the principles of quantum mechanics, this information should never be truly lost, because the laws governing the universe at the quantum level are supposed to preserve information under all circumstances. But Hawking radiation, in its original formulation, appeared to be completely featureless, a thermal glow carrying no detailed information about whatever fell into the black hole. If the black hole eventually evaporates entirely, releasing only this featureless radiation, then the information about everything that fell in would seem to be irretrievably lost, in apparent violation of the fundamental rules of quantum mechanics. This is the information paradox, a deep tension between the theory of gravity and the theory of quantum mechanics, and resolving it has become one of the central challenges in theoretical physics. The various proposed resolutions touch on some of the most fundamental questions about the nature of space, time, and reality, suggesting that information may somehow be encoded in the radiation after all, or preserved at the boundary of the black hole, or that our understanding of how these objects work is incomplete in ways we have yet to grasp. The resolution of the information paradox, whatever it turns out to be, may hold clues to the deeper theory that unites gravity and quantum mechanics, the long-sought framework that would describe the universe at its most fundamental level. For our purposes, though, the essential point is that black holes, the great durable survivors of the cosmos, are not eternal. They radiate, they shrink, and they ultimately evaporate, releasing their substance back into the universe as a thin stream of energy over spans of time that stretch comprehension to its limits. When the last black hole has finally evaporated in its closing burst, the universe will have lost its final structures, leaving behind only a sparse haze of particles and radiation drifting through an enormous and ever-growing void. This brings us to the question of what such a universe is actually like, this end state reached after all the stars have died, all the galaxies dismantled, all the matter dissolved, and all the black holes evaporated. It is a state that physicists describe as the heat death of the universe, a condition of maximum disorder and minimum available energy, and understanding what it means and why it represents a kind of ending requires examining the deep principles that govern energy, disorder, and the very possibility of anything happening at all. The end state that the universe approaches through eternal expansion has a name that sounds paradoxical, given how cold it actually is. It is called heat death, and the term comes not from any notion of warmth, but from the branch of physics that studies heat, energy, and their transformations. To understand what heat death means and why it represents a genuine ending, we have to examine one of the most fundamental and far-reaching principles in all of science. A principle that governs not only the behavior of engines and the flow of heat, but the very possibility of anything interesting ever happening in the universe. This is the principle of entropy, and the law that describes its behavior, the second law of thermodynamics, may be the deepest constraint on the long-term future of the cosmos. Heat death is, in essence, the destination toward which the relentless increase of entropy drives the universe, the state in which entropy reaches its maximum, and the capacity for change is exhausted. Entropy is often described as a measure of disorder, and while this description captures part of the idea, a more precise way to think about it concerns the distribution of energy. Energy can exist in concentrated, organized forms, or it can be spread out in diffuse, disordered forms. A hot object next to a cold object represents a concentration of energy, an ordered arrangement in which energy is unevenly distributed. Left alone, heat flows from the hot object to the cold one, until both reach the same temperature, and the energy that was once concentrated becomes evenly spread out. This evening, out of energy is an increase in entropy, and it is one of the most reliable tendencies in all of nature. Energy spontaneously flows from concentrated to diffuse, from ordered to disordered, from useful to useless. The second law of thermodynamics states that the total entropy of an isolated system always tends to increase over time, never to decrease. Things naturally run down, spread out, and even out, and they never spontaneously organize themselves back into concentrated, ordered arrangements. The crucial insight is that useful work, the kind of energy transformation that makes anything interesting happen, depends on differences, on concentrations of energy that can flow from one place to another. A steam engine works because there is a difference in temperature between the hot steam and the cooler surroundings, allowing energy to flow and do work in the process. A star shines because there is a concentration of energy in its core that can flow outward. Life itself depends on energy gradients, on the flow of energy from concentrated sources like sunlight to more diffuse forms, capturing some of that flow to build and maintain the intricate order of living things. Everything that happens, every process that does work or creates structure or sustains activity, depends on energy being unevenly distributed, on there being differences that allow energy to flow. As entropy increases and energy spreads out evenly, these differences diminish, and the capacity to do useful work declines. When entropy reaches its maximum, when energy is distributed as evenly as possible throughout the system, no further useful work is possible, because there are no longer any differences to exploit. This is the state of heat death, a condition of maximum entropy in which energy is spread out uniformly, and nothing meaningful can happen. Applied to the universe as a whole, this principle implies a remarkable destiny. Throughout cosmic history, the universe has possessed concentrations of energy, the hot cores of stars, the gradients between hot and cold regions, the ordered structures of galaxies and remnants. These concentrations have driven all the activity of the cosmos, the shining of stars, the formation of structures, the processes that gave rise to planets and life. But the second law dictates that these concentrations are steadily being dissipated, that the universe is gradually evening out, spreading its energy more and more uniformly as time passes. The stars burn their fuel and radiate their energy into space, where it diffuses and cools. The remnants leak away their heat. The black holes evaporate, releasing their substance into the void. With each of these processes, the energy of the universe becomes more spread out, more uniform, less capable of doing useful work. The end point of this long dissipation is a universe in which energy is distributed as evenly as possible, a thin, cold, uniform haze in which no concentrations remain, no gradients exist, and no further activity is possible. This is the heat death, the maximum entropy state toward which the eternal expansion drives the cosmos. What would such a universe actually be like? It would be almost unimaginably cold, its temperature having fallen to a tiny fraction above the lowest possible temperature as the energy spread out across the ever-expanding volume of space. It would be almost perfectly uniform, with no significant differences from one region to another, the matter and radiation it contained having dispersed into a thin, featureless haze. There would be no stars, no galaxies, no black holes, no structures of any kind, only the sparse remains of dissolved matter and the faint, cold radiation left over from the evaporated black holes and the decayed remnants, all spreading endlessly through a void that continues to expand. And crucially, there would be no possibility of anything new happening. Without energy gradients, without concentrations of energy that could flow and do work, the universe would be locked in a state of permanent stillness, incapable of forming new structures, sustaining any activity, or supporting anything resembling the processes that fill the cosmos in its active eras. Time would still pass, in some technical sense, but nothing would change, because there would be nothing left to drive change. This is why heat death is considered a kind of ending, even though the universe in this state still technically exists and still contains energy. The point is not that the universe disappears, but that it becomes incapable of doing anything. All the interesting activity of the cosmos, all the processes that create and sustain structure, depend on the entropy being below its maximum, on there being concentrations of energy that can still flow and do work. Heat death is the state in which this capacity has been exhausted, in which the universe has run all the way down and has nothing left to give. It is an ending not in the sense of annihilation, but in the sense of permanent stasis, a final, changeless condition from which nothing new can ever emerge. In this view, the universe does not end with a bang or a collapse, but with a slow, inexorable fading into uniformity, a gradual exhaustion of all the gradients and differences that made activity possible, until at last, nothing remains but cold, featureless, eternal stillness. There is something profound and a little disquieting in this picture, because it suggests that the rich, active, structured universe we inhabit is a temporary phase, a fleeting episode of order and activity in a cosmos destined for permanent stillness. The stars, the galaxies, the planets, life itself, all of these are expressions of the universe's current state of relatively low entropy, its current possession of energy gradients that can drive activity. As entropy increases and those gradients diminish, all of this activity must eventually cease. The universe of structure and change is the exception, a brief flourishing made possible by the low entropy conditions that prevailed in the early cosmos, while the universe of stillness and uniformity is the rule toward which everything inexorably tends. We live, in this sense, during a special and temporary era, a window of activity bracketed by the featureless simplicity of the early universe on one side and the featureless uniformity of heat-death on the other. Yet heat-death is not the only possible ending, and it depends critically on the assumption that dark energy remains constant and that the universe continues its eternal expansion. The heat-death scenario follows naturally from a universe that expands forever, spreading its energy ever more thinly across an ever-growing volume until uniformity is achieved. But if dark energy behaves differently, if it strengthens over time rather than remaining constant, then the universe faces a very different fate, one that arrives not through the slow exhaustion of energy gradients, but through the violent tearing apart of every structure in the cosmos. This alternative ending, driven by an accelerating expansion that grows without bound, would unfold in a manner utterly unlike the gradual fading of heat-death, dismantling the universe not over the almost endless spans of the black hole era, but in a comparatively rapid and dramatic finale. To understand this possibility, we have to consider what would happen if the force driving the cosmic expansion did not hold steady, but instead grew ever more powerful, eventually overwhelming all the other forces that hold the universe together. The possibility that dark energy might strengthen over time leads to one of the most dramatic of all cosmic endings, a scenario in which the accelerating expansion does not merely carry galaxies apart, but eventually tears apart every structure in the universe, down to the smallest scales. This ending is called the Big Rip, and it stands in stark contrast to the slow, gradual fading of heat-death, where heat-death unfolds across almost endless spans of time through the patient exhaustion of energy gradients. The Big Rip would arrive comparatively quickly and would dismantle the cosmos not by letting it run down, but by ripping it apart through an expansion that grows without limit. To understand how this could happen, we have to consider what it would mean for dark energy to behave not as a constant, but as something that intensifies as the universe ages. Recall that dark energy, if it is a true cosmological constant, maintains a fixed density as the universe expands, so that each region of space carries the same amount of dark energy, regardless of how much the universe has grown. This constant density produces the steady acceleration we observe, carrying galaxies apart at an ever-increasing rate, but not tearing apart structures that are held together by their own gravity, like galaxies and solar systems. Within a galaxy, the gravitational binding is strong enough to overcome the gentle push of a constant dark energy, so the galaxy remains intact, even as it recedes from other galaxies. But suppose dark energy is not constant. Suppose instead that its density increases over time, growing stronger as the universe ages. In that case, the push it exerts would not remain gentle, but would intensify, eventually growing strong enough to overcome even the gravitational binding that holds structures together. This kind of strengthening dark energy is described by physicists using the term phantom energy, a form of dark energy whose density rises rather than staying fixed, driving an acceleration that escalates toward a catastrophic conclusion. If dark energy behaves as phantom energy, the consequences for the far future would be severe and would unfold in a characteristic sequence, tearing apart structures in order from the largest and most loosely bound to the smallest and most tightly bound. In the early stages, the effect would resemble the ordinary accelerating expansion, with distant galaxies receding ever faster and disappearing beyond the horizon of observability. But as the dark energy continued to strengthen, its disruptive influence would begin to reach smaller scales. The clusters of galaxies, the great gravitationally bound assemblies that contain many galaxies each, would be torn apart, their member galaxies flung away from one another as the expansion overcame the gravity binding them together. Then the individual galaxies themselves would begin to come apart, their stars and remnants pulled away as the strengthening expansion overwhelmed the gravity that had held each galaxy together since its formation. The grand spiral and elliptical structures that organized matter throughout cosmic history would dissolve, not through the slow evaporation of gravitational encounters, but through the direct action of an expansion grown strong enough to rip them apart. The process would continue to ever smaller scales as the dark energy grew ever stronger. After the galaxies were torn apart, the expansion would begin to disrupt individual planetary systems, pulling planets away from their stars as the binding gravity of each system was overcome. A planet orbiting a star would find its orbit growing wider and wider as the space within the system expanded faster and faster until finally the planet was torn free and cast into the surrounding void. Then the stars and remnants themselves would come under threat as the expansion grew strong enough to overcome even the immense gravity that holds a star or a dense remnant together. The objects that had survived all the previous eras, the durable remnants and any remaining structures, would be pulled apart, their material dispersed as the relentless expansion tore at the very bonds holding them together. And in the final moments, the expansion would grow so violent that it would overcome even the forces that bind atoms together and hold the components of atomic nuclei in place. Matter itself would be torn apart at its most fundamental level, the atoms ripped into their constituent particles. The particles themselves perhaps pulled apart if the expansion grew strong enough, until nothing remained but an infinitely rapid expansion of utterly dispersed components. This sequence, from clusters to galaxies to planetary systems to stars to atoms, would unfold in a characteristic order determined by how tightly each kind of structure is bound. The most loosely bound structures, the great clusters of galaxies, would dissolve first, while the most tightly bound structures, the atoms and their nuclei, would hold out until the very end. And crucially, in the Big Rip scenario, this entire sequence would culminate in a definite moment, a point in time at which the expansion became infinitely rapid, and every structure, no matter how tightly bound, was torn apart simultaneously. This final moment is sometimes described as a singularity, a point at which the expansion rate becomes infinite, and the familiar description of space and time breaks down. Unlike heat death, which is approached gradually and asymptotically across almost endless time, the Big Rip would arrive at a specific, finite moment, a genuine end to the universe as a structured entity, after which the very notion of space, as we understand it, might cease to have meaning. What makes the Big Rip particularly striking is how the final stages would unfold, with the largest structures coming apart well before the end, while the smallest held together until the last instant. In the closing stages before the final moment, the disruption would cascade through smaller and smaller scales in rapid succession. Galaxies would be torn apart. Then, in the remaining time, planetary systems would dissolve. Then stars, and only in the final fraction of the remaining span would atoms themselves be ripped apart. The acceleration of the process means that the bulk of the dramatic dismantling would be concentrated near the end, with the universe appearing relatively normal until comparatively shortly before the final moment, when the cascade of destruction would sweep through all scales in quick succession. An observer in such a universe, if one could exist, would see the cosmos appear stable for most of its history, only to watch the structures around them come apart in an accelerating sequence as the final moment approached, the binding of ever smaller structures failing in turn until the very atoms of their own bodies were torn apart. Whether the universe actually faces a big rip depends entirely on the nature of dark energy, on whether its density remains constant or increases over time. This is a question that observations are actively probing, because the behavior of dark energy can in principle be measured by tracking how the expansion rate has changed throughout cosmic history. If dark energy is a true cosmological constant, the Big Rip cannot occur, and the universe is destined for the gradual fading of heat death instead. But if dark energy is phantom energy, with a density that rises over time, then the Big Rip becomes a real possibility, and the universe would face this dramatic tearing apart at some finite point in the future. Current observations are most consistent with dark energy being approximately constant, which would favor heat death over the Big Rip, but the measurements are not yet precise enough to rule out a slowly strengthening dark energy. The recent hints that dark energy might be evolving rather than perfectly constant have kept the question open, and while those hints have so far suggested a dark energy that might be weakening rather than strengthening, the full picture remains uncertain. It is worth emphasizing how much rides on the precise behavior of a force we still do not understand. The difference between heat death and the Big Rip is the difference between a universe that fades slowly into cold uniformity across almost endless time, and a universe that is violently torn apart at a definite future moment. These are radically different fates, and which one the universe faces depends on subtle properties of dark energy that we are only beginning to measure. The same uncertainty that makes the cosmic future so difficult to predict also makes it a subject of active scientific investigation, with new instruments and surveys designed specifically to pin down the behavior of dark energy and thereby determine which ending awaits. For now, we are left with a range of possibilities, each consistent with some version of the physics we understand, and the resolution awaits better measurements of the mysterious force that dominates the cosmos. But there is yet another possibility, one that arises not from a dark energy that strengthens, but from one that weakens or reverses, allowing gravity to reclaim its ancient dominance and pull the universe back together in a reversal of the expansion that has defined its history. If dark energy were to weaken over time, or even reverse its sign and become a force that pulls rather than pushes, the universe would face a fate entirely different from both heat death and the Big Rip. Instead of expanding forever or tearing itself apart, the cosmos would eventually stop expanding, reverse course, and begin to contract, falling back in on itself in a process that mirrors the expansion that has defined its history. This scenario is called the Big Crunch, and it represents the universe collapsing back toward the kind of hot, dense state from which it originally emerged. The Big Crunch was, for much of the 20th century, considered one of the leading candidates for the fate of the cosmos, back when the question hinged on whether there was enough matter to halt the expansion through gravity. The discovery of dark energy and accelerating expansion made the Big Crunch seem unlikely, but it remains possible if dark energy behaves in certain ways, and it carries with it a tantalizing implication that the other endings lack, namely, the possibility of renewal. To understand the Big Crunch, we have to imagine the expansion of the universe slowing, stopping, and reversing. In the standard picture without dark energy, this could happen if the universe contained enough matter for gravity to eventually overcome the expansion. The mutual gravitational attraction of all the matter in the cosmos would gradually slow the outward rush of the galaxies, much as the gravity of the Earth slows a ball thrown upward. If the matter density were high enough, the expansion would eventually halt entirely, reaching a maximum size before beginning to reverse. Once the contraction began, gravity would accelerate it, drawing everything back together faster and faster. The galaxies, which had spent the expansion phase moving apart, would begin to approach one another, the space between them shrinking rather than growing. Over immense spans of time, the universe would contract, growing denser and hotter as its contents were compressed into an ever smaller volume. In a universe dominated by dark energy, the Big Crunch requires that dark energy not remain constant, but instead weaken or reverse. If dark energy is a dynamic field, rather than a fixed constant, it is conceivable that its density could decrease over time, eventually allowing the gravitational attraction of matter to reassert itself. In some models, dark energy could even reverse its sign, transforming from a force that pushes space apart into one that pulls it together, actively driving the contraction. Either way, the result would be the same in broad outline. The expansion would slow, stop, and reverse, and the universe would begin its long fall back toward density and heat. This makes the Big Crunch dependent on the same uncertain physics that governs all the dark energy scenarios, hinging on whether the mysterious force driving the cosmos is constant, strengthening, or weakening over time. The contraction phase of a Big Crunch would, in many respects, resemble the expansion phase run in reverse, though with important differences. As the universe contracted, the galaxies would draw closer together, eventually merging as the space between them disappeared. The background radiation that fills the cosmos, currently cold and faint, would grow hotter as it was compressed into a smaller volume, gradually warming the universe. In the late stages of the contraction, the temperature would rise dramatically until the entire cosmos was filled with intense heat, the radiation having been compressed to the point where it could ignite and overwhelm everything. The structures of the universe, the stars and remnants, and whatever else remained, would be subjected to ever-increasing temperatures and pressures as the contraction accelerated. Eventually, the heat would grow so intense that matter as we know it could no longer exist, the atoms broken apart by the rising temperatures, the universe approaching a state of extreme density and heat resembling the conditions of its earliest moments. The final stages of a Big Crunch would see the universe compressed toward a state of extraordinary density, with all of its contents crushed together into an ever smaller volume at ever higher temperatures. As the contraction approached its endpoint, the conditions would resemble those of the very early universe, when everything was packed into an incredibly hot, dense state. the familiar description of space and time would break down as the density approached extreme values, and the universe would approach a singularity, a point of effectively infinite density where the known laws of physics cease to apply. This terminal singularity of the Big Crunch would, in some sense, mirror the initial singularity from which the universe is thought to have emerged, the two bracketing the entire history of the cosmos between a fiery beginning and a fiery end. The universe that began in a hot, dense state would end in one as well, its entire expansion and contraction representing a single grand cycle, from density back to density. It is precisely this mirroring of the beginning that gives the Big Crunch its most intriguing implication. If the universe began in a hot, dense state and ends in one, it is natural to wonder whether the ending might also be a beginning, whether the collapse of one universe might give rise to the birth of another. The idea is that the terminal singularity of a Big Crunch, rather than representing a true and final end, might instead serve as the seed for a new expansion, a new beginning that emerges from the collapse, just as our universe emerged from its initial hot, dense state. In this picture, the Big Crunch would not be the absolute end of everything, but a transition, a doorway from one cosmic cycle to the next. The universe would collapse, reach a state of extreme density, and then rebound, beginning a new phase of expansion that would eventually form new structures, new stars, new galaxies, perhaps even new observers who might one day ask the same questions about their own cosmic future. This possibility transforms the Big Crunch from a simple ending into a potential mechanism for cosmic renewal, raising the prospect that the universe might pass through cycles of expansion and contraction without end. Whether such a rebound is actually possible is a deep and unresolved question, because it depends on physics we do not yet understand, the physics of what happens at the singularity where the known laws break down. In the simplest treatment, the singularity represents a genuine endpoint, a state of infinite density where the description of space and time fails completely and beyond which it makes no sense to ask what happens next. But many physicists suspect that this breakdown reflects the limitations of our current theories rather than a true feature of reality. A more complete theory, one that successfully unites gravity with quantum mechanics, might reveal that the singularity is not a true endpoint, but a transition, a point at which the universe passes through an extreme state and emerges into a new phase. Such a theory might describe how a collapsing universe could rebound into a new expansion, avoiding the infinite density of a true singularity and instead bouncing back at some finite, extremely high density. If this is how nature actually works, then the Big Crunch could indeed be a doorway rather than a wall, and the collapse of our universe could give rise to a successor. The Big Crunch then occupies a special place among the possible endings, because it alone naturally suggests the possibility of something afterward. Heat death leads to permanent stillness, and the Big Rip leads to a singular tearing apart. But the Big Crunch, by returning the universe to the kind of state from which it began, opens the door to renewal. This is what makes it so compelling to those who find the prospect of an absolute ending difficult to accept, because it offers a vision of the cosmos as something that might persist through cycles, dying and being reborn in an endless succession of expansions and contractions. But the question of whether a rebound is truly possible, whether the collapse can give way to a new beginning, requires us to look more closely at the models that propose such cycles, the bouncing and cyclic cosmologies that attempt to describe a universe without a single beginning or end. These models, built on the speculative physics of what happens at the moment of collapse, offer some of the most fascinating and ambitious attempts to imagine a cosmos that endures beyond any single ending. The idea that a collapsing universe might rebound into a new expansion has given rise to a family of cosmological models known as bouncing and cyclic cosmologies, which attempt to describe a universe that passes through repeated phases of expansion and contraction, rather than experiencing a single beginning and a single end. These models represent some of the most ambitious attempts in theoretical physics to imagine a cosmos that endures across multiple cycles, and they offer an alternative to the picture of a universe that begins once and ends once. The appeal of such models is considerable because they sidestep some of the deepest puzzles about the origin of the universe by proposing that there was no single origin at all, that the cosmos has been cycling through expansions and contractions for an indefinitely long time, perhaps forever. The basic concept of a bouncing cosmology is that the universe does not begin at a singularity of infinite density, but instead emerges from a previous phase of contraction. In this picture, what we call the beginning of our universe, the hot, dense state that expanded into everything we see, was not truly the beginning, but the rebound point of a prior universe that had been collapsing. Instead of the contraction ending in a true singularity, the universe reaches some extremely high but finite density and then bounces, reversing from contraction to expansion. The bounce avoids the infinite density of a singularity, replacing the absolute beginning with a transition from a previous phase. If this is how the universe works, then the hot, dense state we associate with the beginning was simply the moment of maximum compression between a previous contracting phase and our current expanding phase. The universe would have a history extending before what we think of as the beginning, a history of contraction that preceded our expansion. A cyclic cosmology extends this idea further, proposing that the universe undergoes not just a single bounce, but an endless series of them, cycling through repeated phases of expansion and contraction. In such a model, each cycle consists of an expansion phase, during which the universe grows and forms structures, followed eventually by a contraction phase, during which it collapses back toward high density, followed by a bounce that initiates a new expansion. The cosmos would thus pass through cycle after cycle, each one a complete history of expansion and collapse, with the bounce serving as the bridge between the end of one cycle and the beginning of the next. In the most ambitious versions of these models, the cycles extend infinitely into both the past and the future, describing a universe that has always existed and will always exist, perpetually renewing itself through the eternal alternation of expansion and contraction. There would be no first cycle and no last, only an endless succession of cosmic births and deaths, each universe rising from the ashes of its predecessor. The great challenge for all bouncing and cyclic models lies in explaining how the bounce actually works, how the universe transitions from contraction to expansion without passing through a true singularity where the known laws of physics break down. This is the central difficulty, because in the straightforward application of the standard theory of gravity, a collapsing universe does reach a singularity of infinite density, a point at which the description of space and time fails completely. To avoid this and produce a bounce, something must intervene at extremely high densities to halt the collapse and reverse it into expansion. Various proposals have been put forward for what this something might be, often involving exotic physics that comes into play only at the extreme densities near the bounce, where quantum effects on gravity itself might become important. Some models invoke the idea that at sufficiently high densities, gravity might effectively become repulsive, pushing the universe apart rather than pulling it together, thereby producing the bounce. Others appeal to additional dimensions of space, or to the dynamics of fundamental entities proposed by various approaches to unifying gravity with quantum mechanics. In each case, the bounce depends on physics that goes beyond our well-established theories, physics that we do not yet fully understand, and that operates only under the most extreme conditions. One of the persistent difficulties with cyclic models concerns the buildup of entropy from one cycle to the next, a problem that connects back to the second law of thermodynamics. Recall that entropy, the measure of disorder and the spreading out of energy, tends always to increase. In a cyclic universe, if entropy accumulates from one cycle to the next, then each successive cycle would begin with more entropy than the last, and this buildup would change the character of the cycles over time. The cycles could not be truly identical and repeating if entropy were steadily increasing across them, and tracing the cycles backward would suggest that there must have been a beginning, a first cycle with the lowest entropy, undermining the idea of an eternal cycling universe with no origin. Resolving this problem has required ingenuity, with some models proposing that the universe expands enormously during each cycle, diluting the accumulated entropy so much that each new cycle effectively begins fresh, with the entropy spread so thinly across the expanded volume that it does not impede the next cycle. In these models, the expansion between bounces is so vast that it resets the conditions for the next cycle, allowing the cycling to continue indefinitely without the fatal buildup of entropy that would otherwise bring it to an end. Some cyclic models take a particularly elegant approach by combining the dark energy that drives our current acceleration with the mechanism for cycling. In these scenarios, the accelerating expansion driven by dark energy is not the prelude to an eternal heat death, but rather a phase in a longer cycle. The dark energy drives the universe to expand and dilute, spreading its contents and its entropy across an enormous volume, until eventually the dark energy itself evolves, weakening or changing in a way that allows the expansion to give way to a slow contraction. This contraction then proceeds toward a bounce, which initiates a new cycle of expansion. In such models, the dark energy that we observe today plays a crucial role in the cycling, serving as the agent that dilutes the universe and resets the conditions for the next cycle. The acceleration we measure would then be not a sign of impending heat death, but a stage in an ongoing process of cosmic renewal, the universe spreading itself thin in preparation for its next contraction and rebirth. These cyclic and bouncing models, for all their elegance and appeal, remain speculative because they depend on physics that we have not yet established and that operates under conditions we cannot directly probe. The bounce, the crucial transition that makes cycling possible, relies on our understanding of how gravity behaves at extreme densities, a regime where our current theories break down, and where a complete theory uniting gravity and quantum mechanics is required. Until we have such a theory, the bounce remains a hypothesis, a plausible but unconfirmed mechanism that might or might not describe how nature actually behaves. Moreover, distinguishing cyclic models from the alternative of a single beginning and ending is observationally challenging, because the evidence we can gather about the early universe might be consistent with multiple scenarios. Some cyclic models do make predictions that could in principle be tested, such as subtle features in the patterns of the early universe that would differ from those predicted by other models. And these predictions offer a path toward distinguishing among the possibilities. But for now, the cyclic and bouncing cosmologies remain among the more speculative proposals, intriguing and mathematically developed, but not yet established as descriptions of reality. What these models share is a vision of the cosmos as something that endures beyond any single ending, that renews itself through cycles or bounces rather than terminating in heat death or a final tearing apart. They represent an attempt to answer the question of what comes after the universe ends by proposing that the ending is not truly final, that it gives way to a new beginning in an endless or near endless succession. Whether this vision is correct remains unknown, and it will likely remain unknown until we have a deeper understanding of the physics that governs the most extreme conditions, the densities and energies at which our current theories fail. But the cyclic and bouncing models are not the only proposals for how an ending might give way to a new beginning. There is another idea, even more startling in its implications, which suggests that the cold, empty, maximally expanded universe of heat death might itself, through a subtle reinterpretation of geometry, be equivalent to the hot, dense beginning of a new cosmos. This idea, known as conformal cyclic cosmology, proposes a connection between the end and the beginning that does not require a collapse at all, finding the seed of a new universe in the very emptiness of the old.